This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
A site like Altona or Longford, or other times we just get people from within the business to come and talk to us about what it is that they do within their team. So there's definitely a support network for everyone, and they try and make it really easy for you to understand the business and to learn about it.
We hire technically strong engineers with demonstrated initiative and teamwork skills. And from there are plenty of opportunities to work with like-minded smart people to achieve impressive results.
ExxonMobil hires from their vacation work pool. So I saw this opportunity as a 3-month interview to show the company what I'm made of and my technical skills and abilities. Hopefully at the end of this program there will be a job and a career for myself and also for the other people in the vacation work pool.
Taking a step into our program is a step towards an exciting career.
So I guess the vacation work program we run is over summer. So it's in the summer break between 2019 and 2020. But we are doing at the moment a scholarship called the ExxonMobil Awards for Excellence. So that scholarship, the applications close on Monday, and I'm interviewing next Tuesday for the recipients. In addition to a cash prize, you get basically you bypass the first round of our recruiting process and get a second round interview if you want to take it. There's no obligations. So it's definitely one to look out for. It's open to all penultimate year students in the Masters of Engineering. So basically anyone who's finishing at the end of 2020, because the idea is you do vacation work and then if you're successful in vacation work, we offer you a grad job the following year. So the links are on the Melbourne Uni, on the School of Engineering scholarships page. Should be able to find it there, probably better than I can direct you. And probably the only other thing that I just mentioned is we're having an information session actually tonight, so over the road, where I'll be talking for a little bit, probably playing the same video again, apologies, but talking for a little bit about what it's like to work at Exxon, the vacation work program, and afterwards there'll be some time for Q&A if you had any questions that you wanted answered or anything like that. So probably don't have time for any questions now, but yeah, unless there was one or two quick ones or... No. All right, cool. Thanks, guys. Oh, yeah. I will say one thing, actually, because I sat here in 2012 doing control systems with Professor Cantoni, and I didn't think I was ever going to use much of that ever again. And then the first thing I did at Exxon was working basically as an advanced controls engineer for 3 years, where we were step testing a gas plant. So it is actually, I was highly surprised at how much was basically directly transferable to a real job role. So, yeah, pay attention. Thanks.
Okay, so the plan today is to continue looking at problem set 1, and then we'll move back to part 2 of the notes. Okay, so before we start looking at problem 2, let me just say something about the differential equation models that we were using last time to study this passive vibration control system. So when we were looking at this model, we said, well, it's not linear, okay? And the reason it was not linear was because of these constant terms here, which we didn't want to carry around as signals, right? Because signals are things that are going to be changing across time, and we're using the differential equation model to describe relationships between things that change across time. Whereas these things are constants, so we didn't want to think of them as signals. And by virtue of these constants being here, these equations are not just scaled sums of the signals and their derivatives, right? We've got an extra constant hanging around, which makes the equations affine as opposed to linear. And when you're working with an affine ODE model, so something that takes this form, so let's just suppose that there's only one signal of interest and we're using the differential equation model to just tell us about how that signal behaves rather than its relationship, okay, just for the sake of argument, and that it has this affine form. So if this were not here, then it would be linear, just a scaled sum of the signal and its derivatives, okay, but it's affine because there's a constant here. Then the algebraic function that defines this differential equation model has this form here, right? It's evaluated at Zn equal to the nth order derivative of Z at time t. Zn minus 1 is evaluated at the nth minus 1 derivative. Z1 is evaluated at the first derivative with respect to time. Z0 is evaluated at the signal Z. Okay, it will take this form. And remember, when we're doing linearization, the thing that we approximate is this algebraic function, and we approximate it with the first part of a Taylor series expansion under the assumption that all of the derivatives of arbitrary order with respect to each of these arguments exist. Okay, so that's the form of the algebraic function that we have to approximate when the ODE model takes this form. Okay, it's not quite linear. If this were not here, that would be a linear function of the arguments. Because the constant's there, it's an affine function. Now, if you were to take the Taylor series expansion of this with respect to a nominal value for the arguments, and let's denote those with a subscript q, then you would evaluate the function at the nominal values. That's what that bit is there. Then you would get a sum of the partial derivatives times the difference between the argument and its nominal value. Okay, so that's what you would get there. You could just get to this step by rearranging this equation, right? I mean, you can see that this term here gets cancelled out by this guy here, and we just get alpha n Zn. And the same, this guy here just cancels out this one, and we just get alpha naught Z naught plus k. All right? So in fact, stopping at the after the first term in the Taylor series expansion actually doesn't lead to any approximation at all. Okay, so there's no approximation in taking the first order Taylor series when the function looks like that. All right, and so you can now just replace effectively. This looks like the first part, right? Except now we're going to evaluate it at the incremental version of the signals and its derivative, right? Which is why down here we didn't actually have to do anything when trying to find the relationship between the incremental signals. Effectively, we just had to replace the signals and its derivatives by their incremental versions. Okay? It's like just working with this bit here. Okay? This bit, obviously, if we choose these values to correspond to an equilibrium, is just 0. Okay? So the point is, there is no approximation to be made when the original function is affine. Okay? So that's why we didn't have to do anything last time. Okay? So I just wanted to add that point to the first problem. Okay, the second problem is about modelling the system shown here. It involves an inverted pendulum, okay, which is just an arm with a mass concentrated at the end, okay, and that's driven by a DC motor. So a DC motor is represented by this guy here. This is a schematic description of the system. It helps us perhaps identify the quantities of interest. In this case, the quantities of interest are the angular position of the inverted pendulum, all right, and what we can impose at the terminals of the DC motor, so the voltage that we can apply across the terminals. And we're looking to build a model that describes the relationship between the voltage we can apply across the terminals of the motor and the angular position. All right, to get us there, we are going to use this alternative schematic description of the system that highlights that there is an electrical part of the system, all right, and a mechanical part of the system. All right, so this arm and the motor shaft has a moment of inertia. Okay, we lump that into J. Okay, there's the angular position of the arm. Okay, there's some damping because perhaps there's a gearbox in here, and so that can be approximated with some damping. All right, so that's the mechanical side. Now, the motor produces a torque that acts on the arm. All right, and the torque that acts on the arm will be proportional to the current that flows through the armature windings. Okay, so that of course is the electrical part of the system. All right, we apply a voltage across the terminals. There will be a current that flows through the armature winding. The armature winding will have some resistance, okay, and some inductance. All right, and this represents the so-called back EMF, okay, which is represents a physical phenomenon. I'll explain what that is in a minute. So I'm going to briefly describe the physics of the situation because that helps some people. If you're confused by the physics, just don't pay attention to what I'm saying, right? And focus on how we manipulate the equations to eventually end up with something that describes the relationship between V and theta. All right? So the current flowing through the windings produces a magnetic field that interacts with another magnetic field that may be produced by some permanent magnets inside the motor. Okay? And it's that interaction of the magnetic fields that produces a torque. Okay? And the simple model we're going to use for the relationship between the current and the torque is just a linear model that says that the torque will be proportional to the current. Okay, in a real system, it might be more complicated than that, but for the sake of argument, we're just going to say that that's the model we're going to use. All right. The voltage here represents the fact that as the shaft of the motor turns, okay, the flux linkage, the magnetic flux that links the winding changes, right? Because we're changing the orientation of the windings relative to the permanent magnets, okay? And the rate of change that the rate at which the flux linkage changes will be proportional to the speed that we're moving, all right? So we're getting a rate of change of flux linkage. And Faraday's law says that that will result in an induced electric field, okay? And that induced electric field will result in a change in current that opposes the motion, right? Physical systems always try to oppose what you're trying to do to them, all right? So if we are moving with a particular speed and then we increase the speed of rotation, okay, then the voltage here will change in such a way that the current will change to result in a force that opposes the increase in the speed of rotation. Of course, if there's an increase in the speed of rotation, it's because there's an acceleration. We're only getting acceleration because there's a torque, maybe because something happens here, this changes and it's not resisting as much, starts to speed up, right? There will be a corresponding change in the back EMF that changes the current that opposes that speed up. Okay, so it's just a physical phenomenon that we're representing here, okay? And we're going to take a particular model for the relationship between the back EMF, okay, and the speed of rotation, theta dot. And it happens to be just a non-linear relationship, just plucked out of the air for the sake of argument. All right? We're going to say that the back EMF is minus a constant, positive constant, times theta dot cubed. Okay? Now, of course, the fact that there's a minus sign here relates to the fact that we're choosing a particular sign convention. Sign conventions are completely arbitrary, right? You can choose them in different ways, but once you choose one, you stick to it. Okay, and so we're going to measure the angle as positive in the clockwise direction. All right, and again, just for fun, define the torque produced by the motor as being in the anti-clockwise direction when there's a positive current flowing in the direction shown. Okay, so that a positive current flowing here will produce a torque that can balance the force acting on the mass due to gravity when the angle is positive. All right, but that means that the constant that relates the speed of rotation to the back EMF must be have a negative sign in front of it. Okay, if you chose a different sign convention, you would get a different sign for that relationship. Okay. Like I always say, the physics isn't the key point here. I'm just trying to make the link for those who have an understanding of that because it might help them. All right? But let's just take those objects as being given, or those simple models as being given. All right? So there's a bunch of questions here. We're not going to be able to answer these last two bits because we haven't covered enough material yet. But the first one is about deriving some differential equation models from the basic models that I just described. Okay, and basic models for things like what the voltage drop across a resistor is when there's a particular current flowing through it, and what the voltage drop across an inductor is when the current is changing in a particular way. So I'm going to put all of those basic models together to build a model for the whole thing. All right, and then we're going to linearise, all right, and figure out a transfer function that relates the incremental versions of the signals, all right, in a bunch of steps. So let's just think about the electrical side. So the electrical side can be described by a differential equation that looks like this. That simply follows by applying Kirchhoff's voltage law to the loop that's shown here. Okay, so the voltage that we apply, okay, must equal, whoops, I don't know what happened there, wrong pen. The voltage drop across there, right, which is just R times I, plus the voltage drop across there, which is just L di dt, okay, plus the voltage drop across there, which is the back EMF. All right, so that's where we get this equation from. All right, saying V equals L di dt plus Ri plus VB, and I've just taken VB onto the other side. Now, I mentioned that we're going to use this model for what VB is, right? So by the sign convention that we set up, the back EMF will be minus a positive constant times theta dot cubed. Okay? So that's where this comes from. It's just substituting in that model for the relationship between the back EMF and the angular speed. All right? Now we have the mechanical part plus a model that relates the current in the winding to the torque that acts on the arm. All right? So what we're going to use is a version of Newton's second law for angular motion rather than linear motion. All right? And that just says that the moment of inertia times the angular acceleration will equal the net torque. All right? It's like saying mass times acceleration is the net force, right? But it's just angular motion now. So, this is the moment inertia of the inverted pendulum. Consists of two parts. This part is the moment of inertia for the unloaded DC motor, so with the arm detached, just the rotor. Okay, it has mass, so it has some moment of inertia. All right, this is the moment of inertia of an arm of length L. Okay, so that's the total moment of inertia. And now we need to set that equal to the net torque. Right? Now we've got minus T being the torque produced by the motor. And remember that it acts in the opposite direction to the way we're measuring positive angle. Okay, so that's why it's minus T. All right? This is the torque that acts on the arm because of gravity. Right? So gravity acts down like this. Okay? There will be a component in the direction of the arm and a component in this direction. Right? The component in this direction will be mg sine theta. Right? Times the length of the arm gives you the torque due to gravity acting on the mass at the end of the arm. All right? So that's where this term comes from. All right? And then there's this term here, which if we took it over this side would be minus b theta dot. And that models some viscous damping due to perhaps there being a gearbox. Right? And it, like the damper in the previous example, opposes the motion. Right? Which is why it's minus b theta dot. Okay? If we take it to the right-hand side of the equation, but if we take it onto the left-hand side, it becomes plus b theta dot. Okay, and to go from here to here, we're just replacing this, the torque produced by the motor, by its relationship to the current in the windings. Okay, so that's where those two equations are coming from. They're differential equations that describe the relationship between signals of interest. The signals of interest are the current in the winding, all right, the voltage across the terminals, and the angular position. And we've got two equations that are describing the relationships between those signals in terms of those signals and their derivatives. Okay, so they're just two equations that are describing the relationship between all of those signals. Now, all right, part two is about saying, well, characterise the possible equilibria. At equilibrium, all of the signals are constant. That's what the definition of equilibrium is. All right. The equilibrium constants for all the signals still have to satisfy the differential equation model. All right. But of course, all of the derivative terms in the differential equation model at equilibrium are zero because the derivative of a constant is zero. All right. So for this guy here, right, we get that, R times the equilibrium value of the current, all right, plus L times the derivative of the equilibrium value of the current, which is obviously just zero because the derivative of a constant is zero, right, must equal the constant equilibrium voltage that you apply across the terminals, okay, plus KB times the equilibrium value of theta dot. Well, at equilibrium, theta is a constant, so theta dot will be zero. All right? And you get this equation here. All right? Describing a relationship between the equilibrium value of the voltage across the terminals and the equilibrium value of the current flowing in the windings. Okay? We can do the same thing with this equation. Okay? At equilibrium, that is zero, okay? And we're just left with minus mgl sine equilibrium value of the angle equal to minus kt equilibrium value of the current. Okay? So we could find now an equilibrium relationship between the voltage across the terminals, assuming it's constant, and the corresponding constant angle. All right, by replacing IQ here with VQ divided by R. All right, so I could say, well, I'm going to apply 2 volts across the terminal and keep that constant. The thing will move around and hopefully reach equilibrium. It'll reach equilibrium when the torque produced by the motor balances the torque due to gravity. Right? Once those things balance, there's no net torque on the system, and it will stay where it is. Okay. All right. So now we're looking to find a model that relates incremental versions of our signals of interest relative to equilibrium values. So let's define those incremental versions of the signals as shown here. Okay, so this is how far the current moves away from its equilibrium value, right? This is how far the voltage across the terminals will be wiggled away from its equilibrium value, and this is how far theta will move away from its equilibrium value when we wiggle the voltage across the terminals. Right? We're looking for a model now that relates these new quantities. Okay? And we can get an approximation for that relationship by linearising these differential equations. Okay? So let's look at these differential equations. There's something to note here, right? Is that, we could rewrite this by taking this over the other side and getting something equal to 0, which would be in our canonical form. But even if we did that, what we'd end up with on the left-hand side is a sum of things. Now, when you're linearising a sum of things, you can linearise each component of the sum one at a time and then just add the linearisations together. Right? So you don't have to go through the long process that we've been going through so far, which is the foolproof way of doing it. You can take some shortcuts every now and then by realising that, to linearise a sum of things, you can just linearise the components of the sum and then add them back together again. All right, so that's, shown here. All right, if I have a function of 2 variables, that's the sum of 2 functions, right? My first-order Taylor series approximation of this function is given by evaluating that function at some nominal values, plus the first partial derivative of that function with respect to the first argument evaluated at the equilibrium values times the argument minus its nominal value plus the first partial derivative with respect to the second argument evaluated at the nominal values times that second argument minus its nominal value. Right? So if we write out what those things are, you'll see that this is just F1 evaluated at the nominal value for x plus F2 evaluated at the nominal value for y. This will be this, okay, and this will be this. So that's like, this is the first order Taylor series approximation of this guy, and we're adding to that the first order Taylor series approximation of the next guy. So that's often a shortcut that we can take when we're dealing with a sum of things. Okay, so if one of those functions looks like this, which is already linear, right? Your first order Taylor series approximation is the same thing again. All right, and that would still be true if we added a constant here, which is what we saw at the start of the lecture. All right. If one of the terms in the sum looks like this, right, then the first order Taylor series approximation looks like this. We evaluate it at the nominal value plus the derivative with respect to x evaluated at the nominal value times this. All right, so if it looks like this, we get kx cubed, the nominal value cubed, plus, well, the derivative of this with respect to x is 3k x squared, but we evaluate it at the nominal value and then multiply that by the difference between the argument and the nominal value. Okay, so that's what that looks like. You know, if the function looks like a sinusoid, okay, then the first order Taylor series approximation looks like this, right? We always evaluate the function at the nominal value. That gives us c sine xq plus the derivative evaluated at the nominal value. Well, that'll be c, the derivative of sine is cos, evaluated at the nominal value, xq, times the difference between the argument and the nominal value. And if x, the nominal value is 0 and the function we're looking at is sine, then you get this approximation here. All right? So the small signal approximation of sine is x. Right? So for small values of x, sine just looks like a straight line with slope 1. Okay? So you can use those sort of tricks, all right, to figure out what the linearization of things look like here. Here we've got a sum of things. Here's one of the things that we just saw how to linearize. Right? Here's a sum of things. Here's one of the things that we just saw how to linearize. So now we can put those things together, just add them back together. All right? Okay. So, the linearization of this guy here, right, will just be L delta I dot. Okay? This guy here will be just R delta I. All right? This guy here will be delta V. So really I'm using this, right? All right. Well, and the fact that, well, I'm using it like here, where I'm putting the delta value here and relying on this being some equilibrium value that will balance out the equilibrium values for all the other terms. All right? This is the cubic one, all right, which we saw, linearizes like this, all right, and we get this. But it's important that the derivative term in the linearization gets evaluated somewhere, and we're evaluating it at the equilibrium value for theta dot. But the equilibrium value for theta dot is just 0 by definition, right? So that term goes away. So really what we should be writing here is this is L times the equilibrium value of delta I dot, and this should be R times the, that should be I. Let me rub that out, start again. So I should be adding to this term here L I Q dot, but of course that's 0, right? I should be adding to this term here R I Q, right, so that I can write delta here. I should be adding to this guy delta V, I should be adding VQ, right? And I should be adding to this guy, 3KB theta dot Q cubed, right? But we know that that's 0, and we know that that's equal to that, and so they cancel each other out, and we're just left with what's written there. Okay? We can do the same thing to the other equation. All right? And we end up with this term here because of the way that sine linearizes. Okay? So it's very mechanical if you approach it in a systematic way. All right? So now we have these linear models. We have L delta I dot plus R delta I equals delta V. Okay? That is a linear differential equation that relates delta V and delta I. Okay? So we could just take the Laplace transform of both sides of that equation. Remember, the Laplace transform is something that you do to signals. Well, this is just a signal made out of the sum of some other signals. So we can apply the Laplace transform to that. But if these signals are equal to that, then the Laplace transform of this must equal the Laplace transform of that. All right, so when we take the Laplace transform, we get L. So this will be S delta I S, right, minus delta I0 plus R delta IS. So that's just taking the Laplace transform. And that must be the Laplace transform of the other side. And we're just using capital letters to represent the transform. Okay? Now, it would be reasonable to assume that we're starting at equilibrium. And if we're starting at equilibrium, that's 0. And so we just get SL plus R delta IS equals delta VS. So now I've got a relationship in the frequency domain between the Laplace transform of the incremental version of the voltage signal and the incremental version of the current signal. All right? You can do the same thing for this equation here to get a relationship between the Laplace transform of the current and the Laplace transform of, the Laplace transform of the incremental version of the current and the Laplace transform of the incremental version of the angular position. Okay? So that's where this comes from. And we call this the transfer function from V to I. And the reason that this is the transfer function from V to I is because if I multiply that by delta V as an input, right, then I'm multiplying that by delta V, and they cancel out, and I'm just left with delta I. So this becomes delta IS equals 1 on LS plus R delta VS. And we think of this as the transfer function. Okay? This is what you get when doing the same thing to this equation here. Right? When we take this into the Laplace domain, it will get a relationship between big delta IS and big delta theta. Right? And you get this. So this is the transfer function from delta I to delta theta. All right? Now, ultimately, we want to know the relationship between delta V and delta theta. All right? So we want to figure out, delta theta on delta V. Right? Well, that's going to be delta theta on delta I times delta I on delta V. All right? And so all we have to do is take the product of these two functions to figure out what the transfer function G is from V to theta. All right? So we can't talk about the other parts which relate to stability and steady state values because we haven't covered that part in the notes yet. Okay? I'm going to try to do some of it now. Are there any questions on that? Again, this should be stuff that you've seen before. Maybe not the linearization steps, but at least doing stuff like this you should have done before. Are there any questions on that? No? And the advantage of going to the frequency domain is that things just become algebraic. I got to this by just algebraically manipulating this equation. Right? If I divide both sides by this, that's what I get. Right? So the manipulation of the models becomes purely algebraic. That's the big advantage of going to the frequency domain. Okay? And in the end, we end up with these simple models that relate quantities of interest. The relationships correspond to multiplication by a transfer function. Okay? All right, so let's go back to part 2. Okay, unfortunately, in the last lecture, when I was just trying to cover off on all the properties of Laplace transforms, I forgot to show you this slide here. Okay, it tells you about a relationship between the final value of a signal, so the value taken by a signal as time approaches infinity, when that is a finite value, and its Laplace transform. Okay, so if you know that your signal in the time domain goes to a constant value as t goes to infinity, then that constant value will be equal to the limit as the real part of s goes to 0 from above of s times the Laplace transform of that signal. Okay, so that's sometimes called the final value theorem. Here's a proof for it when we know an exponential bound on how y approaches its final value, right? So we're saying, you know, y is a function of time. We know it approaches a final value. Okay, that's its final value. Let's call that y infinity. And we have this exponential envelope that tells us how it approaches the final value. Okay, and given such information, you can prove this result. All right, so that's the final value theorem. It's a useful thing. The important thing to realise is that it only applies when you already know that the signal goes to a constant final value. If you don't already know that, you cannot apply this theorem. So you first have to verify that the signal in the time domain goes to a constant value as time goes to infinity. If you know that that's the case, okay, then that final value must bear this relationship to the Laplace transform. And there's a corresponding initial value theorem as well. Okay, and here's the proof for that. If the proof makes your head explode, don't worry about it. Okay, it's there because it helps some people. All right, but the key thing to remember here is that you can't just apply these results willy-nilly. You need to know that the limits already exist. Okay. All right, so now let's look at another example that's related very closely to the thing we just looked at from the problem sets. Okay. So this is a DC motor driving some inertial load. Okay, there's an electrical part and a mechanical part of the system. All right. The linearised motor equation tells us that the torque produced by the motor is proportional to the current flowing through the windings. Okay, the current flowing through the windings produces a magnetic field in proportion to the current that interacts with another magnetic field to produce a torque, right? And here's how we're modelling that relationship. Okay, Newton's second law for angular motion tells us that the moment of inertia times the angular acceleration is equal to the net torque. Right? The torque produced by the motor relates to the current in the way shown here, and this models some viscous damping. Okay, the viscous damping always corresponds, resists the motion, like pulling a damper through the fluid inside the box. Right? If I pull this way, it's pulling back. It's opposing the motion. That's why we end up with a minus sign there. Okay. Kirchhoff's voltage law around here just tells us that the voltage across the terminals here must equal the drop across this plus the drop across this plus the drop across this. The drop across here is telling us about the back EMF. All right? So we get this differential equation model. This is just showing what those look like in the frequency domain. All right? And it just happens here that we've already got linear models. Right? All of these things are just scaled sums of the signals of interest and their derivatives. All right? So we can take them into the frequency domain by taking the Laplace transform of each side. Remember, the Laplace transform is something that we do to signals. This is a signal made up of a sum of other signals. Okay? When you're taking Laplace transforms of derivatives, you have to carry around initial conditions. Okay? Often those initial conditions are 0 because we assume that the system starts at rest or starts at equilibrium. Okay? And if we assume, in this case, that all initial conditions are 0, then putting all of these things together in a fashion similar to what I just showed for problem 2 in problem set 1, okay, you end up with this expression for the transfer function from the input voltage to the angular position. Okay, if I multiply this by u, what do I get? Theta, right? So this is the transfer function. And if I multiply u by the transfer function, I get theta out. Okay, this is just emphasising how you can get this as the transfer function from these objects here. All right. So if I substitute this in here, I get a relationship between I and theta, as I did before. This is now giving me a relationship between u, I, and theta, but given the relationship between I and theta, I can eliminate I and just end up with an equation that relates u and theta, and rearranging that gives me this. Now, it's often convenient to re-express transfer functions in the form shown here. Okay? Now, what is this? It's the ratio of two polynomials. The top is a 0th order polynomial. It's just a constant, right? That constant is the motor constant that relates the current and the torque. The bottom is a cubic polynomial in S. Okay, if I multiply that out, that's quadratic, and then I'm multiplying it by S. It's cubic. All right? And all I'm doing here is re-expressing this divided by this quadratic in a new way. All right? This is still a quadratic. Times S gives me the cubic object on the bottom. Right? I've just reparameterized it. And I've reparameterized it in a way that's convenient, as I'll show shortly. So how do you go about finding the new parameters, K, T, 1... Whoops, what happened there? What's happened? Okay. That's convenient. Let's go there, and then go there. There we go. I don't know what happened there. Sorry about that. So how do we go about finding these new parameters, given the original parameters? Right, the original parameters are the motor constant, all right, the viscous damping constant, the inductance, the resistance, the moment of inertia, okay, and so forth. Sorry, that was the back EMF, that's the damping one. So you find these by just taking this equation, right, and then getting this equation from that by taking this up to this side and this up to this side, right? So I get a cubic equal to a cubic, right? This cubic involves mainly the new parameters, right? And this one mainly involves the old ones. So I can find equations describing the new parameters by just matching coefficients, right? So, if I match the coefficient of S, and that's the lowest power of S that we have, because we've got these guys out the front. Okay, so if I match the first power of S, okay, I'm saying that times 1, right, which is K2, must equal that times this. And there's one equation that straight away tells me what my new parameter K is in terms of the old parameters. Okay? Now I match the coefficients of S squared. Right? And the coefficients of S squared are this times this, okay, which is this guy here. And on the other side, I've got this times this. Okay, so that gives me another equation. Right? I know what K is, so really this is an equation in T1 and T2. And now I match the coefficient of S to the power of 3. And the coefficient of s to the power of 3 is this times this, and this times this. Okay, so that gives me another equation, right? Once I eliminate k here and express it in terms of the original coefficients, then I've just got two equations in two unknowns, right? And I can solve. All right? Now, you end up having to solve a quadratic equation, and that may not always have real solutions. All right? But if this inequality holds for the original parameters, then the new parameters T1 and T2 will be real valued. Okay, so when you solve these two equations for the two unknowns, T1 and T2, you'll get real values. Okay, so it's just a reparameterization, and it follows by some simple algebra. Okay. So now that we have this reparameterized version of the transfer function, we can get yet another representation of that transfer function as a sum in this form. And the advantage to having a sum in this form is that we know that things that look like this in the Laplace domain look like exponentials in the time domain, right? So we saw that e to the minus at looked like 1 on s plus a, all right? But 1 on s plus a is, you can take the a out the front and you get 1 on a s plus 1, which now looks like this form here, all right? And it's why you get the 1 on t term in the exponential, all right? So the advantage to splitting up like this as a sum of objects that look like this is because we know what these translate to in the time domain. Things like this, with a first order polynomial on the bottom, take us to exponential signals in the time domain, right? This guy here, we saw, is just really the Laplace transform of a unit step function scaled by the constant a1. Okay? So remember that this is the transfer function, right? But the transfer function is the Laplace transform of the impulse response. That was something we saw in the last lecture. And so going to this signal in the time domain is telling us what the impulse response looks like. It tells us how the system responds if I just whack it, right? And what will come out is a sum of a step and two decaying exponentials. All right? Now, how do I get to this reparameterized form? Well, you just do partial fraction expansion, right? How does partial fraction expansion work? Well, it works like this. It's not hard to work out what those parameters are. So let's just work with something that looks like this, where we've got a factor like this, right? When we've got something like this, we can always represent it like this, as the sum of two bits. The first bit has this on the denominator. The second bit has this on the denominator. When we add those two things together, we get something with the product of these things in the denominator, right? And on the top, we'll get a times d plus m times this factor here, right? And that must equal n of s. But instead of trying to match coefficients, okay, if we just rewrite this expression like this by taking the 1 on ts factor outside, then we see that in order for this to be equal to this, this must be equal to this, right? Which is all I've written down here. And now if we evaluate this at s equals minus 1 on t, you get 0 here, which then tells you that a must be this evaluated at s equals minus 1 on t. So that gives you effectively, the cover-up type rule, right? So to get this coefficient here, right, you just multiply this by s and then evaluate it at s equals 0. And that gives you a1 equal to k. To get this coefficient here, you multiply this by t1s plus 1, right? That'll cancel out that. And then you evaluate what's left over at s equals minus 1 on t1, and so forth. I hope you've all learnt how to do partial fraction expansion before. That's all that's happening here. All right? So what's the advantage of expressing it in this way? Well, it's just the sum of these exponentials. All right? They're shown in this picture here. Okay? Each component. Just bear with me for 5 seconds. All right? So you get the sum of these components. The speed with which the exponential things decay depends on this